If we think back at this unit, we could classify collisions in a number of different ways. We could classify one-dimensional collisions as rear-end collisions or as head-on collisions. We could classify 2D collisions as T-bone or glancing collisions. We could classify collisions as one-dimensional or two-dimensional collisions. But today we're going to learn a different way of classifying collisions, and it's not going to be based on momentum at all. The reason we're not going to classify these collisions based on momentum is because in any kind of collision, however we classify it, momentum is conserved. It's not a very good classification system if every single one of them fits in one category. We're going to today define two different types of collisions. One is called an elastic collision, in which, of course, momentum is conserved, because momentum is always conserved if we have an isolated system. But in an inelastic collision, kinetic energy is also conserved. So in other words, not only do you not lose momentum in this isolated system, but you don't lose kinetic energy either. The final kinetic energy will be equal to the initial kinetic energy. Now, I'll be honest with you, the vast majority of collisions that take place, momentum is conserved, of course. Kinetic energy is not conserved in the vast majority of collisions. In the vast majority of collisions, we have kinetic energy lost. We lose kinetic energy. We have what we call an inelastic collision, in which momentum is still conserved, but kinetic energy is not conserved. Kinetic energy is lost. If you've got a guess on a question, and I hope that doesn't happen, I hope you just know the answer to a question without guessing, but if you've got a guess whether a collision is elastic or inelastic, guess inelastic. Because probably 80 or 90% of the time, collisions are, or at least 80 or 90% of the time, collisions are inelastic. If you're going to guess, take a 90% chance of being right versus a 10% chance of being right. Now, why is it that most collisions are inelastic as opposed to elastic? I want you to think back to grade 10. You learned two laws of thermodynamics. One of them says that energy can't be created or destroyed, only transformed. Remember that one? The other one says that you can't even break even. In other words, when you convert energy from one type to another, you always lose a little bit in the process of converting it. Remember that? If you don't remember that, all right, that's okay. Now I'm telling you. Okay, you always lose a little bit of energy when you convert energy from one type to another. All right, so let's use an example here. Let's bounce a basketball. Bounce a basketball on the floor. That basketball, when it hits the floor, will change direction and bounce back, right? What happens to that basketball as it hits the floor? Yep. Okay, some of the energy would be lost to sound. Absolutely, absolutely. That's not what I was looking for, but you're absolutely right. What happens to the basketball itself as it hits the floor? It compresses, it squishes. When the basketball squishes or compresses, you're converting kinetic energy that it has just as it hits the ground to elastic potential energy as the ball squishes. And then it gets converted back to kinetic energy as it goes back up into the air, right? And then gravitational potential. So you got a couple of different conversions taking place there. Every time one of those conversions takes place, what happens? We lose a little bit of energy. Therefore, the final kinetic energy can't be as much as the initial kinetic energy. That's why in the vast majority of collisions, it'll be inelastic, because in the vast majority of collisions, we get a little bit of squishing taking place. And whenever you have that squishing taking place, there's a conversion of energy taking place. And when you have a conversion taking place, the final can't be as much as the initial. Does that make some sense? Give me an example of a situation where we don't get very much squishing. In other words, where the collision might be elastic or real close to elastic. We got a few curlers in the room. When two curling rocks hit each other and bounce off of each other, they squish a little bit. Those rocks compress a little bit, but not very much, right? In an immeasurable amount, which means that if they don't compress hardly at all, then the kinetic energy doesn't get converted to potential and then back to kinetic. It just stays kinetic. And if the kinetic energy isn't converting, then we're not going to lose any in the process of converting. Therefore, it would be either elastic or really, really close to elastic. The only time we have truly an elastic collision, like billiard balls, curling rocks, they're close. The only time we have truly elastic, where there is absolutely no kinetic energy loss because we have absolutely no compression and energy conversion taking place. Anybody want to take a stab at it? Somebody in the last class got it. The only things that can't compress are the only things that are as small as they can possibly get. Somebody said, somebody's on the right track. What'd you say? Subatomic particles, right? Subatomic particles like electrons, if they collide, they don't get any smaller, right? It's fundamental. It doesn't get smaller than that. So they can't compress. If they're as small as they already can get, then they can't compress, and therefore you don't have an energy conversion taking place. Therefore, when they collide, you're not going to lose kinetic energy. It's going to be elastic. Look, the vast majority are inelastic. If you've got to guess inelastic. The exception to that would be subatomic particles that are elastic. So you get a subatomic question, you got to guess. You might want to guess that's elastic. Otherwise, guess inelastic. Okay, I'm going to give you a little bit of a potential shortcut. When two objects hit each other and they stick together, that will be inelastic. So that's going to help us to avoid doing a calculation. If they stick together, we know that kinetic energy will be lost every single time, always. No calculation necessary. Kinetic energy is going to be lost. Now, we don't know how much kinetic energy is going to be lost, but we know kinetic energy is going to be lost. Two objects bounce apart. Well, if they bounced apart, it could be elastic sometimes, but it could also be inelastic. If I had to guess, I would guess inelastic because usually that would be the case. So if they bounce apart, you don't know. If they stick together, you know. You never know when you look at a question that it's for sure elastic, but if they stick together, you do know for sure that it's inelastic. If you're not sure, do a calculation, and we'll see that calculation, what that calculation involves in just a couple of minutes here. Remember though, ideally you don't have to guess, but if you do have to guess, you're going to guess inelastic. All right, let's take a look at an example here, a mathematical example to show us how this works here. Question says, a 2,000 kilogram truck traveling north at 20 meters per second collides with a 1,500 kilogram car traveling south at 12. They entangle it, they head off as one. Is it elastic or inelastic? Tell me right now, quick, answer. Elastic or inelastic? Inelastic. It's inelastic because they stick together. Now, I'm going to go through the mathematical justification of this just to show you that, in fact, it is inelastic. The kinetic energy is lost. But if this is a test question, I would not, unless it says justify it, I would not go through a calculation. I would say if they stick together, it must be inelastic. Yep. No, that's not enough to tell me that it's inelastic. No. The fact that they stick together definitely is, but the speed of the truck or the mass of the truck initially, okay, that doesn't give me any indication at all. All right, so here's what we're going to do. We're going to say EKI, the initial kinetic energy, is equal to 1/2 of m1 v1 I squared plus 0, because the second object is at rest. Notice I did not do this, EKI equals EKF, like I do with conservation of momentum. How come? Why would I not set EKI equal to EKF? Isn't? They head off together. We know it's inelastic, right? Why would we set EKI equal to EKF when we know we're going to lose kinetic energy? Even if we didn't know that, we still don't want to set them equal to each other because we didn't know whether they're equal to each other or not, right? We set PI equal to PF because we know the momentum is conserved. But with kinetic energy, don't ever set them equal to each other unless you know it's somehow it's elastic. All right, let's calculate this initial kinetic energy. 2,000 kilograms times V1I is, what, 20 meters per second? 20 squared is 400. 400 times 1,000 is 4.0 0 times 10 to the 5 joules, 4.0 times 10 to the 5 joules. Now let's get the final kinetic energy here. EKF is going to be equal to 1/2 m1 v1 f squared plus 1/2 m2 v2 f squared. 1/2 of 2,000 times, oh, wait a second here. Wait a second, I missed something. That second car is not at rest, is it? That second car was moving south at 12. So this is wrong. So we're going to say 1/2 of 2,000 times 20 squared plus 1/2 of 1,500 times 12 squared. Okay, let's figure out what that is on our calculator here. Say 0.5 times 2,000 times 20 squared. Let's add to that, use some brackets here. 0.5 times 1,500 times 12 squared gives me a value of 5.08, or we're going to round that to 2 digits, 5.1 times 10 to the 5. There's my initial kinetic energy. 2 digits, right? 2 digits because of these. Now my final kinetic energy is 1/2 of 2,000 times, oh wait, messing this up completely here, right? How many objects do we have afterwards? So let's just call it 1/2 mvf squared. One half mvf squared. One object, right? One object, one term. The mass, the combined mass is going to be 3,500 kilograms. And the final speed is 6.28. Oh, don't tell me. Did I make another mistake? Isn't this supposed to be negative 12 meters per second because it's south? How come? Well, even if you square it, it's going to be positive, right? But I don't even want to put a negative in there to begin with. How come? Because kinetic energy is a scalar. Direction doesn't matter, right? Not only does it not matter, I just, like, it's wrong to include it. Like, even though if you put negative 12 and squared it, you would get positive 144, the same number. It's still technically wrong because you don't include direction with a scalar. Okay, let's calculate this. Let's say 0.5 times 3,500 times 6.28 squared gives me 6.9 times 10 to the 4. Look, kinetic energy was lost. Since the initial kinetic energy is greater than the final kinetic energy, then it must be inelastic. I'm going to tell you right now, I've given you several hints on your first written response test, which still isn't coming up for a few weeks here. But when that happens, you're going to see a question involving a collision. You're going to have to solve for a number of things. I've told you a few of those already. One more thing you're going to have to do is show that it's inelastic. You got a collision where these two cars hit each other. I'm going to tell you right now it's inelastic, but you're going to show mathematically that it's inelastic. And you're going to do that by calculating the initial kinetic energy and the final kinetic energy. And then you're going to say, since kinetic energy is lost, it is inelastic. Okay? Now, could you ever see a situation where the two kinetic energies would be the same, 5.1 and 5.1? Yeah, you could. It doesn't happen very often, but you could. What would you say if you got a kinetic energy that was 6.9 times 10 to the 5, greater than the initial kinetic energy? What would you say then? Say energy was gained? I could think of a better answer, though. I made a mistake. That's what I'd say, because kinetic energy won't be gained. If you have an explosion where we have 0 kinetic energy to start, and then you have something, kinetic energy to end, kinetic energy is gained. But we don't classify explosions as elastic or inelastic. We only classify collisions as elastic or inelastic. And in collisions, kinetic energy will either stay the same or it'll be lost. You can't gain. Make sense? All right, let's do one more. Then we'll wrap it up for the day here. This one says a 5 kilogram ball traveling east collides with a 6 kilogram stationary ball. Immediately afterwards, the lighter one goes off at 0.6 at 50 degrees, and the heavier one goes off at 0.63 at 38 degrees, elastic or inelastic. Hey, they bounce apart. Could it be elastic? Conceivably. It could be, yeah. Probably not, but it could be. Let's calculate EKI. We're still not setting EKI equal to EKF. Now, at the risk of messing this up again like I did the last question, I'm going to set the initial kinetic energy of the second one equal to 0, because it is at rest. So we're going to say 1/2 of 5 times 0.98 squared. That's it. The initial kinetic energy is going to be is going to be 2.4 to 2 digits, 2.4 joules. And we're going to find the final kinetic energy. 2 objects this time. So we're going to have 2 terms. Oh, what do I do for this? I'm telling you, I'm going to have to go do those X and Y components again. As much as they're not crazy hard once you get the hang of it, it's still a pain in the butt to do them, right? Cameron, what are you saying there? No? Yeah. Right. So we're just going to say the speed is 0.60. I don't care that the angle is 50 degrees north of east. Remember we said we don't like funny angles? We don't. But this is that guy in the club that's off in the corner. We don't really care. Like we don't like him, but he's not getting in the way of anything, so let's leave him there. Uh, 6 kilograms is our second mass, and 0.63 is our second speed. Again, the direction doesn't matter there. Even though we don't like the funny angle, like it's not bothering us, like it's not doing anything to us. Let's calculate this now. Let's say 0.5 times 5 times 0.6 squared. Let's add that to brackets. 0.5 times 6 times 0.63 squared. We end up getting 2.1, 2.09, 2.10. It's funny actually. This one actually is, no, that's 2 digits as well. 2.1. Look, it's close, hey? Like we didn't lose that much kinetic energy at all. But did we lose some? So it's inelastic. It doesn't matter if we lose a little bit or a lot, it's still inelastic. Now, here's a question I've gotten from people in the past. What if this question was to be rounded to 1 digit? Like what if some of our data was 1 digit and I had to round this to 1 digit and I got 2 and 2? What would I say then? To 1 significant digit, it is elastic. But this question isn't supposed to be to 1 digit, it's supposed to be to 2. So that's what I'm going to round it to, and that's how I'm going to make my judgment. All right? Since kinetic energy, your conclusion is, since kinetic energy is lost, it is inelastic. Right? When you get a question involving momentum, don't forget signs. Don't forget funny angles. If it's 2-dimensional, X and Y component every single time. But if you get a problem involving kinetic energy like this, like it's so much easier. Drop the signs, drop the angles, drop anything to do with direction. You're good.